In the history of humanity, there has never been a journey this quiet. No roaring engines, no spotlight. Just two small spacecraft, leaving Earth and continuing onward, year after year, drifting farther from the familiar light of the sun. They were launched in the late 1970s, at a time when technology was modest and computers were far less powerful than the smallest devices we carry today. And yet, from that moment forward, the two Voyager spacecraft began a journey unlike anything before it. A journey so long that generations of people have been born, lived their lives, and passed on, while Voyager continues to move steadily through space. If you're listening on a quiet evening, wherever you may be on Earth, you're welcome to leave a short comment sharing where you're listening from. Just a simple note, so we know that in this moment, others are sharing the same silence. And if you'd like to return for more journeys like this, subscribing makes it easier to find your way back whenever you need a slower pace or a calmer night. Voyager carries more than scientific instruments. It carries the sounds of Earth, images of human life, and a simple message that we were here. There is no plan to return, no final destination waiting ahead. Only steady motion, quiet persistence, and decades of silence stretching outward. Tonight we'll travel alongside these two spacecraft, not in a hurry, not with noise, just listening to the story of the loneliest explorers in history. In the early 1970s, space exploration was entering a quieter phase. The first great milestones had already passed. Humans had walked on the moon. The drama of the space race was fading, and budgets were tightening. Yet beneath the surface, something unusual was taking shape. Scientists had noticed a rare alignment of the outer planets, a configuration that would allow a single spacecraft to visit multiple worlds using gravity itself as a kind of invisible engine. This alignment would not return for more than a century. If humanity wanted to take advantage of it, the opportunity was now. At that moment, technology was limited by modern standards. Computers filled rooms and operated with less power than a basic digital watch today. Data traveled slowly. Memory was scarce. Every component had to be carefully justified. Yet within those constraints, engineers and scientists began to imagine a mission that would reach far beyond anything attempted before. Not a short visit, not a single destination, but a long, open-ended journey outward, past the known planets, and eventually beyond the Sun's domain altogether. That idea became Voyager. From the beginning, Voyager was different from earlier missions. It was not designed to orbit a planet or return samples. It would not come back to Earth. Its purpose was to observe, to measure, and to keep going. The spacecraft would pass by Jupiter and Saturn, and in the case of one of them, continue onward to Uranus and Neptune. After that, there would be no planned encounters, only distance. Voyager was meant to follow a path that did not loop back on itself. It would move forward steadily, without an endpoint written into the design. In the history of space exploration, this marked a subtle shift. Earlier missions focused on destinations. Voyager focused on passage. It was built not around arrival, but around endurance. Space rarely gives us simple answers, and Voyager was not sent to answer a single question. It was sent to keep asking. The scientific goals were ambitious but grounded. Voyager would study planetary atmospheres, magnetic fields, radiation environments, rings and moons. It would observe how charged particles flowed through space and how the sun's influence changed with distance. Each measurement was modest on its own, but together they formed a picture of how the solar system functioned as a connected system rather than a collection of isolated worlds. This approach reflected a growing understanding that space is not empty, but structured. shaped by forces that extend far beyond what the eye can see. At the same time, Voyager carried something less technical and more human. Mounted to the side of each spacecraft was a golden record containing sounds, images, and music from Earth. It was not designed for scientists. It was not expected to be found. It served no practical function at all. Instead, it represented an idea that exploration is not only about collecting data, but about acknowledging presence. Silence is also a kind of data, and Voyager would eventually travel into a silence deeper than any spacecraft before it. Why then did humans feel compelled to go so far? Part of the answer lies in curiosity, but that is only the surface. Beneath it is a deeper pattern that appears throughout human history. When the edge of the known world becomes visible, people feel drawn toward it. Not out of urgency, and not always with clear purpose, but because the unknown exerts a quiet pull. Voyager emerged from that impulse. It was not driven by fear or competition. It was driven by patience. There was also a scientific reason to go farther. Until Voyager, everything humanity knew about the outer solar system came from telescopes and brief glimpses. Jupiter and Saturn were visible as distant giants, but their true complexity remained hidden. Uranus and Neptune were little more than points of light. Voyager offered a chance to see these worlds as systems, with weather, structure, and motion unfolding in real time. Numbers whisper more than they speak. And Voyager was designed to listen. Yet, perhaps the most remarkable aspect of the mission was how it was built to last. Engineers understood that Voyager would operate in environments no spacecraft had experienced. Extreme cold, weak sunlight, increasing distance from Earth. Instead of designing for a specific lifespan, they designed against failure itself. Redundancy was built into nearly every system. Components were simplified. Software was written to be flexible, capable of adaptation decades later. Voyager was not designed to be fast or powerful. It was designed to be resilient. In this sense, Voyager became a kind of experiment. Not only a scientific experiment, but a philosophical one. What happens if a machine is built with care, patience, and humility? What happens if it is allowed to continue without pressure to conclude? Voyager tested whether longevity itself could become a form of discovery. Each year it survived extended the mission into new territory, both physically and conceptually. As the spacecraft traveled farther from the Sun, it also traveled farther from certainty. Communication delays grew longer, signals weakened, data returned more slowly. Engineers learned to value small measurements, subtle changes, and quiet confirmations. The mission gradually shifted from dramatic encounters to careful monitoring. This was not a decline. It was a transformation. Voyager was teaching scientists how to pay attention over long timescales. In many ways, Voyager reflected the era that created it. The 1970s were marked by uncertainty, transition, and reassessment. Grand promises were giving way to more measured expectations. Voyager did not promise answers that would change everything overnight. Instead, it promised continuity. It promised to keep going, long after the headlines faded. And so Voyager left Earth, not as a hero, and not as a symbol of conquest, but as a witness. A small, steady presence moving through a vast system, recording what it could, and remaining functional simply by not giving up. It did not know where it would end. It did not need to. Its value lay in motion, not arrival. As the years passed, Voyager became something rare in modern science. A mission that slowed down instead of speeding up. A project that grew quieter with time. and in that quiet, it revealed a different way of understanding the universe. Not through sudden breakthroughs, but through accumulation, through patience, through persistence. The deeper Voyager traveled, the more it demonstrated that exploration does not always require bold gestures. Sometimes it requires staying operational. Sometimes it requires listening. Sometimes it requires accepting that meaning emerges gradually, far from the moment of launch. And perhaps that is why Voyager still matters. Not only because of what it discovered, but because of how it continues, moving outward, sending back whispers of information, existing as proof that endurance itself can be a form of knowledge. The universe does not rush, and Voyager, in its quiet persistence, learned to move at the same pace. When engineers began working on Voyager, they faced a problem that had no precedent. No spacecraft had ever been asked to operate for decades, traveling farther than any machine before it, without maintenance, without repair, and without the possibility of rescue. The usual question of how long a system should last felt inadequate. Instead of asking how many years Voyager needed to function, the team asked a quieter, more unusual question. How do you design something so that it simply does not break? This mindset shaped every aspect of the mission. Voyager was not designed with a planned expiration date. There was no point on a timeline where it was expected to stop working. The goal was not longevity measured in years, but reliability measured in behavior. Each system needed to continue performing its role under conditions that could not be fully predicted. Extreme cold, weak power, radiation, vast distance, space rarely gives us simple answers, and Voyager's designers knew they would need to prepare for uncertainty rather than control it. At the heart of this philosophy was simplicity. Components were chosen not because they were the newest or fastest, but because they were stable and well understood. Moving parts were minimized. Circuits were designed to tolerate variation. Software was written conservatively, with room to be updated from Earth decades later. Voyager did not rely on fragile precision. It relied on margin, extra capacity, extra time, extra patience. One of the most important design principles was redundancy. Nearly every critical system aboard Voyager had a backup, and often a backup for the backup. There were duplicate computers, duplicate communication paths, duplicate sensors. If one component failed, another could quietly take its place. This was not efficiency in the modern sense. It was resilience. The spacecraft carried more than it strictly needed, not to perform better, but to survive longer. This approach extended beyond hardware. Power management, thermal control, and communication were all designed to degrade gracefully. As the spacecraft moved farther from the Sun and its power supply weakened, instruments could be shut down one by one, prioritizing the most essential measurements. Voyager was not expected to operate at full capacity forever. It was expected to adapt. Silence is also a kind of data, and even as instruments went quiet, the spacecraft continued to tell scientists something valuable simply by remaining alive. Much of this philosophy can be traced to the leadership behind the mission, particularly John Cassani, the Voyager project manager during its critical development years. Cassani was not driven by spectacle. He was known for emphasizing discipline, clarity, and long-term thinking. He understood that Voyager would leave the world of short missions and enter a domain where human schedules no longer applied. Decisions made during development would echo decades later, long after the original team had stepped away. Cassani and his colleagues approached Voyager with humility. They accepted that they could not predict everything the spacecraft would encounter. Instead of trying to outsmart the unknown, they focused on building systems that could tolerate it. This required resisting pressure to optimize for immediate performance. It required saying no to unnecessary complexity. It required trusting that slow, careful design would matter more than impressive specifications. The engineering team also understood that Voyager would outlive them. Many of the people who built the spacecraft knew they would never see the mission's end. This created a subtle shift in responsibility. Voyager was not built for recognition or short-term success. It was built as a message to the future, both scientific and human. Numbers whisper more than they speak. And the quiet reliability of Voyager would eventually speak louder than any single discovery. As the years passed, this philosophy proved itself again and again. Systems that were expected to last a few years continued operating for decades. Software written in the 1970s was still executing instructions far beyond its original scope. Engineers on Earth learned to communicate with a spacecraft that responded slowly, carefully, and predictably. The mission became a dialogue across time, connecting people who had never met, separated by generations. Meanwhile, other spacecraft came and went. Missions ended as planned. Satellites were decommissioned. Probes completed their objectives and shut down. This was not failure. It was design. Voyager was different. It remained, not because it was immortal, but because it was never told when to stop. The question of why Voyager is still operating today does not have a single answer. It is the result of thousands of small decisions made with restraint. Choosing robustness over speed, choosing redundancy over elegance, choosing patience over ambition. Each decision on its own seemed modest. Together they created a spacecraft capable of surviving in conditions that no one fully understood at launch. There is also a human element that cannot be separated from the engineering. Voyager continues to function because people continue to care. Teams at NASA still monitor its signals, still adjust its systems, still find ways to extract meaning from faint data streams. The spacecraft is far away, but it is not forgotten. Its survival is not only technical, it is relational. Over time, Voyager has become something more than a machine. It is a demonstration of a particular way of thinking about technology. One that values continuity over disruption. One that accepts limits instead of fighting them. One that understands that lasting systems are not built by chasing perfection, but by planning for imperfection. As power slowly diminishes, instruments are turned off with care. Each shutdown is a small farewell, not a crisis. The mission narrows, but it does not collapse. Voyager continues to send signals, faint but coherent, shaped by decisions made decades earlier. It does not rush. It does not demand attention. It simply continues. In a world accustomed to rapid change and short cycles, Voyager offers a different lesson. That durability can be intentional. That simplicity can be powerful. That designing something not to fail may be more meaningful than designing it to excel. And perhaps that is Voyager's quiet legacy. A reminder that endurance is not accidental. It is chosen step by step, long before it is tested. The spacecraft moves onward, still functioning, still responding, still present, carrying with it the idea that sometimes the most remarkable achievement is not how far you go, but how long you remain capable of listening. From the outside, launching two nearly identical spacecraft might seem excessive. One well-built probe, carefully tested, could have carried out the mission. But the Voyager program was shaped by a different kind of thinking. Engineers and scientists understood that when a mission stretches across decades and billions of miles, certainty becomes fragile. In that environment, reliability does not come from confidence, it comes from options. That is why Voyager was never a single spacecraft. From the beginning, it was a pair. Voyager 1 and Voyager 2 were built together, tested together, and launched only weeks apart. They shared the same basic design, the same instruments, and the same philosophy of endurance. But they were not duplicates in purpose. They were partners in strategy. Each spacecraft carried the same capabilities, yet each was sent along a different path with different responsibilities. This was not redundancy as backup alone. It was redundancy as exploration. The decision to fly two spacecraft addressed a simple reality. Deep space does not allow second chances. Once a spacecraft leaves Earth, there is no repair crew waiting beyond the moon. If something fails, the mission does not pause. It simply ends. Space rarely gives us simple answers, and Voyager's planners chose to respond not with optimism, but with preparation. Having two spacecraft immediately doubled the odds of success. If one failed early, the other could still return valuable data. If both survived, their combined observations would create a richer picture of the solar system. Even subtle differences in timing and trajectory could reveal patterns that a single probe might miss. Voyager was designed not just to see, but to compare. The two spacecraft followed different trajectories through the outer solar system. Voyager 2 was launched first, on a longer, more complex path that allowed it to visit all 4 giant planets. Voyager 1 followed a faster route, optimized for a close encounter with Saturn's moon Titan before heading outward. These paths were not interchangeable. Each reflected a specific scientific priority. Together, they formed a layered approach to exploration. Voyager 1 became the pathfinder. It moved ahead, reaching key destinations sooner, testing systems and revealing unexpected conditions. Voyager 2 followed behind, informed by what Voyager 1 had already encountered. This sequence allowed scientists to adjust expectations, refine analysis, and interpret results with greater confidence. Numbers whisper more than they speak, and having two streams of data made those whispers clearer. But the most important aspect of this dual mission emerged over time. As the spacecraft traveled farther from Earth, they gradually separated not only in space, but in context. They encountered different regions of the heliosphere at different times. They crossed boundaries under different solar conditions. What one spacecraft experienced, the other might confirm years later. This turned redundancy into validation. In this way, Voyager 1 and Voyager 2 became a living system of checks and balances. If one instrument recorded an anomaly, the other could offer perspective. If one signal weakened unexpectedly, engineers could compare it to the other. Silence is also a kind of data. And sometimes the absence of a signal in one place meant more when it was still present in another. The idea that simply having two spacecraft was itself a form of redundancy proved to be one of Voyager's greatest strengths. This was not redundancy in the narrow sense of spare parts. It was redundancy in experience. Two machines traveling separately, extending the mission's relevance across time and space. Even today, decades after launch, the fact that both spacecraft are still operating provides scientists with a rare opportunity to study change itself. There is also a human dimension to this strategy. Voyager's team understood that no single group of scientists would accompany the mission from start to finish. People would retire, new engineers would join. Knowledge would be passed along, imperfectly. The presence of two spacecraft helped bridge those transitions. When one probe encountered something unexpected, lessons could be applied to the other. The mission became intergenerational, supported by continuity rather than control. As years turned into decades, Voyager 1 and Voyager 2 slowly took on distinct identities. Voyager 1 became the first to leave the heliosphere and enter interstellar space. Voyager 2 followed later, providing confirmation that this boundary was real, measurable, and dynamic. Without both spacecraft, the crossing might have remained ambiguous. Together, they transformed a single event into a scientific understanding. What began as a practical engineering decision evolved into a deeper principle. Exploration is stronger when it is shared. Not shared loudly, but shared quietly, through comparison, patience, and persistence. Voyager demonstrated that resilience does not always come from building something stronger. Sometimes it comes from building more than one. As the two spacecraft continue their separate journeys, they no longer travel together in any meaningful sense. They are far apart, drifting through different regions of space, sending faint signals back to Earth. Yet they remain connected by design, by intent, and by the strategy that launched them. Two paths, two roles, one mission still unfolding. And perhaps this is the quiet lesson of Voyager's dual nature. That redundancy is not wasteful when it preserves meaning. That having more than one voice allows us to listen more carefully. That understanding often emerges not from a single measurement, but from the space between them. Voyager 1 and Voyager 2 continue outward, separated by distance, united by purpose, reminding us that sometimes the most enduring systems are those that are never alone. Voyager 1 was launched with a clear and focused purpose. Its primary mission was to explore Jupiter and Saturn, two worlds that had long fascinated astronomers yet remained only partially understood. Telescopes could reveal their colors and motions, but not their fine details. Voyager 1 was sent to pass close enough to observe these planets directly, to measure their magnetic fields, atmospheres, and surrounding environments, and then to continue onward while its systems remained functional. At this stage of its journey, Voyager 1 was still very much within the Sun's influence, moving through a region of space shaped by solar wind and familiar gravitational patterns. The encounter with Jupiter marked the mission's first major test. As Voyager 1 approached the giant planet, it revealed a world far more complex than expected. Jupiter's atmosphere showed intricate bands and storms layered in constant motion, shaped by forces that extended deep beneath the visible clouds. The spacecraft detected intense radiation belts, confirming that Jupiter's magnetic environment was both powerful and hazardous. These observations helped scientists understand that Jupiter was not simply a large planet, but a dynamic system capable of influencing space far beyond its visible disk. One of Voyager 1's most surprising discoveries at Jupiter was the presence of a thin ring encircling the planet. Before Voyager, rings were associated almost exclusively with Saturn. Jupiter was not expected to have one. Yet Voyager's instruments detected a faint structure composed of fine particles, likely originating from material ejected by nearby moons. Alongside this discovery, Voyager 1 identified two previously unknown moons, later named Thebe and Metis. These small bodies, orbiting close to the planet, helped explain the source of the ring material and expanded the known architecture of the Jovian system. Numbers whisper more than they speak, and these subtle measurements quietly reshaped planetary science. After Jupiter, Voyager 1 continued on towards Saturn, carrying with it the accumulated knowledge from its first encounter. The Saturn flyby was carefully planned as it would shape the rest of the mission. Saturn presented a very different environment. Its rings were broader, more complex, and structured in ways that had only been hinted at before. Voyager 1's observations revealed fine divisions, waves, and interactions between ring particles and Saturn's moons. What had once appeared as a simple, flat structure became a living system governed by gravity, motion, and resonance. Voyager 1 also discovered several new moons orbiting Saturn. These small worlds, embedded within or near the rings, played active roles in shaping ring structure through gravitational influence. Their presence confirmed that moons and rings were not separate features, but parts of a single, evolving system. The spacecraft also identified a new ring, later designated the G ring, adding yet another layer to Saturn's already intricate surroundings. Space rarely gives us simple answers, and Saturn's complexity reminded scientists that even familiar planets can hold unexpected depth. Throughout these encounters, Voyager 1 remained within the heliosphere, the vast region dominated by the Sun's magnetic field and solar wind. Although it was traveling far from Earth, it was still operating within a space environment shaped by our star. Communication delays increased, but the spacecraft responded reliably to commands. Its instruments continued to function, and its data flowed steadily back to Earth. Voyager 1 was still part of the solar system's internal conversation, measuring variations that were connected, directly or indirectly, to solar activity. Behind these scientific achievements lay an important strategic reality. Voyager 1 was not alone. Voyager 2 followed on a different trajectory, observing many of the same regions under slightly different conditions and at different times. This pairing was intentional. The presence of two spacecraft allowed scientists to distinguish between local anomalies and broader patterns. If Voyager 1 detected a feature at Jupiter or Saturn, Voyager 2 could later confirm, refine, or challenge that observation. The mission was built on the understanding that having two perspectives increases confidence. In this sense, the existence of two spacecraft was itself a form of redundancy, not just in hardware, but in understanding. Voyager 1's planetary encounters were not dramatic moments of conquest or triumph. They were careful passages, measured in hours and days, where instruments gathered data and then moved on. The spacecraft did not stop. It did not linger. It passed through these systems as a visitor, collecting what it could and continuing forward. Silence is also a kind of data, and once the encounters ended, the spacecraft returned to quieter observation, its discoveries unfolding slowly through analysis back on Earth. By the time Voyager 1 completed its Saturn flyby, its role within the mission was becoming clearer. It had fulfilled its primary planetary objectives and demonstrated that its systems could endure extreme environments. It had revealed new structures, new moons, and new questions, and it had done so while remaining firmly within the Sun's extended domain. The journey ahead would be different, quieter, and more abstract, but it was built upon these early encounters. Voyager 1's path through Jupiter and Saturn showed what careful design, patient observation, and restrained ambition could achieve. It proved that exploration does not require permanence at a destination. Sometimes it requires only a brief, attentive passing. And as Voyager 1 continued onward, leaving the familiar giants behind, it carried with it the knowledge that even within the known boundaries of the solar system, the universe still rewards those who observe slowly and listen closely. After completing its encounters with Jupiter and Saturn, Voyager 1 faced a quiet but consequential decision. The spacecraft could not visit every destination. Fuel was limited, gravity dictated the available paths, and each choice carried permanent consequences. Engineers and scientists chose a trajectory that would send Voyager 1 upward and outward, away from the plane of the planets, on a path that would eventually lead it beyond the Sun's domain. This decision marked a turning point. Voyager 1 would no longer be a visitor moving from world to world. It would become a traveler leaving home. At first, the change was subtle. Voyager 1 continued to operate much as it always had, sending back data, responding to commands, measuring its environment. Yet its surroundings were slowly changing. The familiar structure of the solar system began to thin. Planetary encounters were behind it. Ahead lay a region defined not by solid worlds, but by invisible forces. Space rarely gives us simple answers, and the spacecraft was now entering a realm where boundaries were gradual rather than sharp. To understand what Voyager 1 was approaching, scientists focused on a vast structure known as the heliosphere. The heliosphere is a bubble created by the Sun itself, formed by the constant outflow of charged particles known as the solar wind. This wind streams outward in all directions, carrying the Sun's magnetic field with it and pushing against the surrounding interstellar medium. For billions of miles, this flow dominates the space around the Sun, shaping the environment through which planets and spacecraft travel. As Voyager 1 moved farther away, the solar wind gradually weakened. The spacecraft began to detect subtle changes in particle density, magnetic fields, and radiation. These were not dramatic signals. They were small shifts, measured patiently over time. Numbers whisper more than they speak, and it was through these quiet measurements that scientists began to sense that Voyager 1 was approaching the edge of the Sun's influence. There is no physical wall at the boundary of the heliosphere. Instead, there is a transition region where the outward pressure of the solar wind balances against the pressure of interstellar space. Beyond this region, particles and magnetic fields are no longer dominated by the Sun. They belong to the galaxy itself. Voyager 1 was designed to notice this change, not by sight but by feeling its environment through instruments that measured plasma, magnetic orientation, and cosmic radiation. For years, the data remained ambiguous. Some measurements suggested the boundary was near. Others indicated that Voyager 1 was still inside. This uncertainty was not a failure. It reflected the true nature of the boundary, which shifts and breathes with solar activity. Silence is also a kind of data, and the absence of clear markers forced scientists to listen more carefully, to compare patterns over long periods rather than rely on a single moment. Then, gradually, the evidence aligned. Voyager 1 detected a sharp increase in high-energy cosmic rays originating from outside the solar system, accompanied by a decrease in particles associated with the solar wind. The magnetic field showed a change in character, signaling that the spacecraft was no longer immersed in the Sun's extended atmosphere. Voyager 1 had crossed into interstellar space. There was no celebration at the spacecraft itself. No signal marked the crossing. Voyager 1 did not know it had left the solar system. The recognition came slowly, through analysis and confirmation back on Earth. Scientists debated, compared data, and waited for consistency. When consensus finally emerged, it was not announced as a dramatic breakthrough, but as a careful conclusion. Voyager 1 had become the first human-made object to enter the space between the stars. By this time, Voyager 1 was more than 3 decades into its journey. Many of the people who had designed and launched it were no longer working on the mission. Others had taken their place, inheriting systems and knowledge passed down through documentation and mentorship. The spacecraft itself became a bridge between generations, carrying decisions made long ago into a future no one could fully imagine. Now, Voyager 1 operates in an environment unlike any it has encountered before. The particles it measures originate from distant stars and ancient events, The magnetic fields reflect the structure of the galaxy rather than the influence of the sun. Communication delays stretch to many hours. Signals are faint. Commands are simple. Yet the spacecraft continues to respond, continuing its quiet work far beyond the reach of familiar space. Voyager 1's departure from the solar system did not mark an end. It marked a shift in perspective. The mission moved from exploring places to exploring conditions, from observing planets to observing space itself. The data it sends back no longer describe worlds, but context, the background against which all worlds exist. In this long, silent phase of the mission, Voyager 1 demonstrates a different kind of achievement. Not speed, not power, but persistence. It continues outward, carrying with it the imprint of human curiosity and restraint. It does not rush. It does not seek attention. It simply continues to measure, to transmit, to exist. And perhaps that is the quiet meaning of this crossing, that leaving home does not always require a destination. Sometimes it requires only the willingness to keep going, to listen carefully, and to accept that understanding unfolds slowly, far beyond the last familiar light. Long after Voyager 1 had completed its planetary encounters and begun its outward journey, a quiet request emerged from Earth. Scientists wondered whether it might be possible for the spacecraft to turn its cameras back toward home, even as it was already billions of miles away. The maneuver carried no scientific necessity. It would not reveal new data about planets or particles. Yet the idea persisted. If Voyager was leaving the solar system, perhaps it could offer one last look back. The result was an image unlike any taken before. From the edge of the solar system, Voyager 1 captured a photograph of Earth as a single, faint point of light suspended in a vast field of darkness. The planet did not dominate the frame. It did not glow brightly. It appeared as a tiny blue speck, barely distinguishable from the surrounding space. This image would later become known as the pale blue dot. Scientifically, the image was simple. The Earth occupied less than a pixel. It was recorded through scattered sunlight, filtered by the spacecraft's instruments, at a distance so great that familiar continents, oceans, and clouds disappeared entirely. From that vantage point, Earth was not a world of detail, but a signal, a reflection, a presence barely strong enough to register, and yet this simplicity carried meaning. From a scientific perspective, the pale blue dot illustrates scale with clarity that numbers alone often cannot convey. Distances measured in millions and billions of miles are difficult to grasp intuitively. But a single pixel, isolated against darkness, communicates proportion immediately. Numbers whisper more than they speak, and this image whispered something profound about size, distance, and perspective. The photograph also marked a shift in the Voyager mission itself. Until that moment, the spacecraft had been looking outward, toward planets and space ahead. This was one of the last times it would turn its attention back toward the inner solar system. Afterward, its cameras were shut down to conserve power, and Voyager's work would become quieter, focused on particles and fields rather than images. The pale blue dot stands as a pause, a moment of reflection embedded within a long trajectory. Beyond its scientific context, the image carries a philosophical weight that unfolds slowly. Every human story, every city, so every conflict, every act of kindness that has ever occurred on Earth exists within that tiny point of light. From Voyager's distance, none of it is visible. There are no borders, no landmarks, no signs of importance. Space rarely gives us simple answers, but it offers perspective without commentary. The Earth, seen this way, appears fragile. Not fragile in a dramatic sense, but in a quiet one. Its atmosphere is invisible. Its protection against radiation and cold cannot be seen. Its ability to support life is not obvious. The planet does not announce itself. It simply reflects a small amount of sunlight and remains suspended in space, vulnerable yet persistent. At the same time, the image carries a subtle sense of connection. That faint dot contains everyone who has ever looked up at the night sky. The spacecraft that took the photograph was built there. The people who interpreted the image lived there. The signal carrying the data returned to antennas on that same tiny point of light. Even at such distance, the loop remained unbroken. Silence is also a kind of data. The vast darkness surrounding the pale blue dot emphasizes how alone Earth is in its immediate neighborhood, yet also how connected it remains through physics, light, and motion. The emptiness is not hostile. It is simply present. Voyager does not judge the scene. It records it. The timing of the image adds another layer of meaning. Voyager 1 captured the pale blue dot as it was preparing to leave the solar system's familiar structure behind. The photograph serves as a quiet threshold, a final acknowledgement of origin before entering a region where Earth would no longer be distinguishable at all. After this point, the sun itself would eventually fade into just another star. For viewers today, the pale blue dot often evokes mixed emotions, a sense of smallness, a sense of humility, sometimes a sense of loneliness, yet these feelings are not separate. They coexist. The image does not diminish human experience. It places it within a larger context. It reminds us that meaning does not come from size or dominance, but from awareness. In the flow of a long Voyager narrative, this moment naturally slows the pace. There is nothing to analyze quickly, nothing to resolve. The image invites stillness. It encourages the listener to rest with the idea of distance, to allow scale to settle in the mind without urgency. Voyager's journey continues, but this moment asks us to pause. As the spacecraft moved onward, the pale blue dot remained behind, not physically, but conceptually. It became part of how we understand exploration itself, not as an escape from Earth, but as a way of seeing it more clearly. From far away, without detail or drama, Earth becomes what it has always been. A small place where connection happens. And perhaps that is the quiet lesson this image offers, that even when we feel alone in the vastness, we are still part of a shared point of light, moving together through a universe that does not rush, asking us only to notice and to remember where we began. When Voyager 2 began its journey, it carried a role that was both practical and quietly ambitious. It was designed to follow Voyager 1, not to repeat its work, but to extend it. Where Voyager 1 moved quickly toward a specific set of objectives, Voyager 2 was given a broader path and a longer timeline. Its task was to observe carefully, to confirm what had already been glimpsed, and to reveal what only patience could uncover. In this way, Voyager 2 became less of a pathfinder and more of a surveyor, moving steadily through the outer solar system with an eye for structure rather than spectacle. The encounter with Jupiter was Voyager 2's first major opportunity to fulfill this role. By the time it arrived, scientists already had valuable data from Voyager 1. Jupiter was known to be a planet of immense complexity, with powerful magnetic fields, intense radiation, and a family of moons interacting in subtle ways. Voyager 2 approached this environment with the advantage of context. It did not arrive to surprise, but to observe with greater clarity. Among its contributions at Jupiter was the identification of an additional moon, bringing the total number of known Jovian moons higher than before. This discovery, modest in scale, carried broader implications. Each small moon helped scientists understand how material moved within Jupiter's gravitational influence and how rings and dust were replenished over time. Numbers whisper more than they speak, and these incremental findings added depth to an already complex picture. Voyager 2's measurements of Jupiter's environment also allowed scientists to compare conditions across time. Differences in particle density and magnetic activity revealed that Jupiter was not static. It responded to solar influence and internal dynamics in ways that changed over months and years. This ability to compare rather than merely observe transformed Voyager 2 into a reference point, a steady observer against which variation could be measured. After Jupiter, Voyager 2 continued on to Saturn, where its role as a surveyor became even more apparent. Saturn's rings had long captivated human attention, appearing elegant and orderly from a distance. Voyager 1 had already revealed their complexity, but Voyager 2 expanded this understanding through detailed measurement and comparison. It observed the fine structure of the rings, noting gaps, waves, and variations in density that suggested constant motion and interaction. These ring structures were not random. Voyager 2's data showed that Saturn's moons played an active role in shaping the rings, creating gravitational resonances that organized particles into patterns. The rings were not passive ornaments. They were dynamic systems, changing slowly but continuously under the influence of nearby bodies. Space rarely gives us simple answers, and Saturn's rings demonstrated how even seemingly stable features are the result of ongoing processes. Voyager 2 also measured Saturn's magnetic environment and plasma interactions, providing insights into how the planet exchanges energy with its surroundings. These measurements complemented those taken at Jupiter, allowing scientists to compare two giant planets with similar compositions but different behaviors. The contrasts mattered as much as the similarities. Together they help define what it means to be a gas giant, not as a category, but as a spectrum of conditions. Throughout these encounters, Voyager 2 moved with quiet consistency. It did not rush. It did not focus on dramatic moments. Instead, it collected data across wide regions, building a framework rather than a snapshot. This approach reflected the mission's broader philosophy. Voyager 2 was not meant to be the first to arrive. It was meant to be the one that stayed attentive. There was also a human rhythm to this phase of the mission. Teams on Earth worked with long delays, planning commands carefully and waiting hours to see the results. Decisions were made conservatively. Adjustments were small. Each successful transmission reinforced trust in the spacecraft's design and in the strategy that sent two probes rather than one. Silence is also a kind of data, and the steady absence of failure became meaningful in its own way. By the time Voyager 2 completed its observations of Saturn, its identity within the mission was firmly established. It was the spacecraft that confirmed, compared, and extended. It transformed individual discoveries into patterns and helped scientists see the outer solar system as a connected environment rather than a sequence of isolated encounters. This careful surveying prepared Voyager 2 for what lay ahead. Its path would soon take it to worlds no spacecraft had ever visited, where comparison would be impossible and context would have to be built from first principles. But its early work at Jupiter and Saturn laid the foundation. It taught scientists how to listen for subtle changes, how to value consistency, and how to find meaning in gradual accumulation rather than sudden revelation. As Voyager 2 moved onward, leaving the familiar giants behind, it carried with it not just data, but a method. A way of exploring that favored patience over speed and understanding over surprise. In the quiet record of its measurements, the outer solar system began to reveal itself not as a collection of destinations, but as a system unfolding slowly, waiting for those willing to observe without hurry. When Voyager 2 left Saturn behind, it entered a phase of the mission unlike anything that had come before. Ahead lay Uranus and Neptune, distant worlds that had never been visited by a spacecraft. Everything known about them came from faint telescope observations and careful inference. There were no close-up maps, no direct measurements, no reliable expectations. Voyager 2 was not traveling to confirm existing knowledge, it was traveling to create it. The encounter with Uranus marked humanity's first close look at an ice giant. From a distance, Uranus appeared calm and uniform, a pale sphere tilted dramatically on its side. Up close, Voyager 2 revealed a world shaped by extremes. The planet's unusual tilt caused its seasons to stretch across decades, bathing one hemisphere in prolonged sunlight while the other remained in extended darkness. This orientation influenced everything from atmospheric circulation to magnetic behavior, offering scientists a new way to think about how planets respond to geometry as much as composition. Voyager 2 discovered 10 previously unknown moons orbiting Uranus, each contributing to a system that was far more intricate than expected. These moons varied in size and character, suggesting a history of collisions, accretion, and gradual reshaping. Alongside them, Voyager 2 identified 2 new rings, adding to a growing understanding that ring systems are not unique to Saturn, but a natural outcome of gravitational processes throughout the solar system. Numbers whisper more than they speak, and these quiet discoveries expanded planetary science in lasting ways. Uranus also surprised scientists with its magnetic field, which was offset from the planet's center and tilted relative to its rotation. This unusual configuration produced complex interactions between the planet and surrounding space, challenging existing models of planetary magnetism. Space rarely gives us simple answers, and Uranus demonstrated that even fundamental forces can behave in unexpected ways when conditions shift. After Uranus, Voyager 2 continued on to Neptune, a planet even farther removed from the Sun's warmth and light. Neptune was the final major destination of the Voyager mission and the most remote planet ever visited by a spacecraft. Expectations were cautious. Scientists anticipated a cold, quiet world. What Voyager 2 found was something more dynamic. Neptune's atmosphere revealed powerful winds and rapidly changing weather patterns. Among its most striking features was a massive storm system, later referred to as the Great Dark Spot, a region of high atmospheric activity comparable in scale to storms seen on Jupiter. This discovery challenged assumptions about how energy moves through planetary atmospheres so far from the Sun. It suggested that internal heat plays a greater role than previously thought, sustaining activity even at vast distances. Voyager 2 also discovered several moons around Neptune, each adding to the planet's story. Some exhibited unusual orbits, hinting at past gravitational interactions or capture events. The spacecraft identified ring structures as well, faint and incomplete, shaped by the delicate balance between gravity and motion. Silence is also a kind of data, and the subtlety of these rings spoke volumes about the processes shaping distant worlds. By the time Voyager 2 completed its Neptune flyby, it had accomplished something unique. It had provided humanity's only close-up observations of 2 planets that remain largely unchanged in our understanding today. No spacecraft has returned to Uranus or Neptune since. not because they lack scientific value, but because reaching them requires time, patience, and commitment on a scale that is difficult to sustain. The distances involved are vast. A mission to the outermost planets takes decades to complete. Technology evolves faster than mission timelines. Budgets shift, priorities change. Voyager 2 benefited from a rare alignment of opportunity, timing, and intent that has not yet repeated itself. Its journey stands as a reminder that exploration is shaped not only by curiosity, but by circumstance. There is also a deeper reason why no spacecraft has returned. Voyager 2 did its work quietly and thoroughly. It gathered enough data to reshape planetary science and left behind questions that require new tools and new approaches to answer. Its legacy is not incomplete. It is open-ended. Numbers whisper more than they speak, and Voyager's data continues to inform models, simulations, and future mission concepts decades later. As Voyager 2 moved beyond Neptune, it left the planetary phase of its mission behind entirely. There would be no more close encounters, no more first views. Yet the significance of what it had done did not diminish. It had expanded the known boundaries of the solar system and shown that even the most distant worlds are active, complex, and worthy of attention. In the quiet aftermath of these encounters, Voyager 2 became something rare, a witness to places that remain unseen, a reference point for knowledge that cannot yet be refreshed. Its observations are not replaced by newer images or updated measurements. They remain foundational, shaping how we imagine these distant planets and how we plan for future exploration. As the spacecraft continued onward, carrying its instruments into colder and quieter space, its discoveries settled into the scientific record. Uranus and Neptune became more than names. They became environments, systems, places shaped by forces both familiar and strange. Voyager 2 did not linger. It moved on, leaving behind understanding rather than presence. And perhaps that is the quiet meaning of this phase of the journey, that some places are visited only once, not because they are forgotten, but because the act of reaching them carries enough weight on its own. Voyager 2 showed us that exploration does not always repeat itself. Sometimes it simply passes through, leaving clarity behind, and trusting that future generations will know when it is time to return. Voyager 2's passage through the outer solar system was not a series of stops, but a continuous motion. The spacecraft did not arrive and remain. It passed by briefly, moving at speeds that made lingering impossible. Each planetary encounter lasted only days or hours, yet each one reshaped human understanding in ways that would endure for generations. Voyager 2 did not revisit these worlds. It did not circle back. Its path moved forward only, carried by momentum established at launch and guided by gravity rather than intention. Flying past a planet at interplanetary speed is a delicate experience, both technically and conceptually. Voyager 2 approached each world along a carefully calculated trajectory, balancing distance and risk. Too far, and details would be lost. Too close, and radiation or gravitational forces could overwhelm the spacecraft. Engineers planned these encounters years in advance, knowing that once Voyager 2 arrived, there would be no opportunity to adjust in real time. Commands sent from Earth took hours to reach the spacecraft. The encounter would unfold on its own. As Voyager 2 approached Jupiter, the sense of scale became immediately apparent. The planet's immense gravity dominated the surrounding space, accelerating the spacecraft and bending its path. Instruments recorded data continuously, capturing changes in magnetic fields, particle densities, and radiation levels. The flyby was fast, but the environment was intense. Jupiter was not simply a destination, it was a force. From Jupiter onward, the distances between worlds increased dramatically. Saturn lay far beyond, separated by years of travel through empty space. During these long stretches, Voyager 2 operated quietly, checking in with Earth through faint radio signals. Its systems ran steadily. There were no images to capture, no dramatic events to record. Silence is also a kind of data. The absence of change confirmed that the spacecraft remained healthy, continuing its long transit through the solar system's outer reaches. The flyby of Saturn introduced a different rhythm. Saturn's gravity reshaped Voyager 2's trajectory more gently than Jupiter's, and the ring system offered an environment of intricate motion rather than raw power. The spacecraft passed through a region shaped by countless particles moving in resonance, guided by moons whose influence extended far beyond their visible surfaces. The encounter was brief, yet dense with information. Voyager 2 moved on, leaving behind a detailed record of a system in constant balance. Beyond Saturn, the solar system opened further. Uranus and Neptune were separated not only by distance, but by time. Voyager 2 traveled for years between encounters, crossing regions where the Sun's influence weakened steadily. The spacecraft's speed remained high, yet from a human perspective, the journey felt slow. Progress was measured in incremental updates, in small adjustments to power and instrumentation, in patient waiting. When Voyager 2 finally reached Uranus, it entered a world unlike any previously visited. The flyby was precise and fleeting. There was no opportunity for a second look. The spacecraft passed once, collecting what it could, and then moved on. The data returned from Uranus carried the weight of singularity. These measurements would not be refreshed or confirmed by another mission anytime soon. Numbers whisper more than they speak, and scientists learn to listen carefully to what this brief encounter revealed. The final planetary flyby at Neptune carried a quiet sense of closure. Voyager 2 approached the most distant planet in the solar system, knowing that this would be the last time any spacecraft would do so for the foreseeable future. The encounter unfolded smoothly, almost gently, despite Neptune's powerful winds and dynamic atmosphere. The spacecraft recorded what it could, then continued onward, leaving the planetary realm behind entirely. Each of these flybys shared a defining characteristic. They happened once. There was no repetition, no rehearsal, no second chance. Voyager 2's journey through the outer planets represents a sequence of events that will not be repeated in the same way again. The alignment of planets, the timing of technology, and the patience required to sustain such a mission converged briefly and then passed. This uniqueness carries scientific significance. Without repeated visits, the data from Voyager 2 remains foundational rather than comparative. It defines baselines rather than trends. Scientists cannot easily observe how these systems change over decades at close range. Instead, they rely on Voyager's brief snapshots, combined with distant observations, to infer long-term behavior. Space rarely gives us simple answers, and Voyager 2's flybys remind us that some knowledge arrives only once. There is also a human dimension to this singular journey. Voyager 2 was built by people who understood that they were creating something that would outlast their involvement. The flybys were planned by teams who would never witness their full consequences. The data was analyzed by scientists who inherited the mission midstream. Voyager 2's path became a shared responsibility across time, carried forward by trust rather than control. As the spacecraft moved from planet to planet, it carried no awareness of history or uniqueness. It followed physical laws, responding to gravity and momentum. The meaning of its journey emerged only through interpretation. Each flyby became part of a narrative constructed later, a story of exploration that unfolded slowly, long after the spacecraft had moved on. The silence between encounters was as important as the encounters themselves. Voyager 2 spent far more time traveling through empty space than observing planets. During these long intervals, the spacecraft's steady operation became a form of reassurance. Its continued presence confirmed that long-distance exploration was possible, that systems designed with care could function reliably across decades. Silence is also a kind of data, and Voyager 2's quiet persistence spoke clearly. Today, when we look back on Voyager 2's planetary journey, it stands apart not because it was dramatic, but because it was complete. It reached every major destination available to it. It did not fail mid-course. It did not require rescue or revision. It moved through the solar system as intended, gathering knowledge and then moving beyond it. The realization that these flybys will not be repeated adds weight without urgency. It does not create loss, it creates appreciation. Voyager 2 reminds us that some moments in exploration are singular, not because they are fragile, but because they are rare. They occur when opportunity, patience, and intent align. As Voyager 2 continued outward, leaving the planets behind, its journey became quieter still. Yet the legacy of its flybys remained, shaping how humanity understands the outer solar system. Each encounter, brief and unrepeatable, contributed to a broader picture that continues to guide science today. And perhaps that is the calm truth revealed by this journey. That exploration does not always depend on return. Sometimes it depends on presence, even if brief. A single passage, carefully observed, can carry enough meaning to last far longer than the moment itself. Once Voyager passed beyond the familiar structure of the solar system, its mission entered its quietest phase. There were no planets ahead, no flybys to prepare for, no dramatic changes expected on short timescales. What remained was space itself. Not empty space, but the space between stars, shaped by particles, fields, and slow-moving processes that unfold far from immediate notice. Voyager's role shifted from exploration by encounter to exploration by presence. In interstellar space, Voyager studies conditions that cannot be measured near Earth. It observes high-energy cosmic rays that originate beyond the Sun's influence. Particles accelerated by distant stars, supernova remnants, and galactic processes that occurred long before human history. These particles move through the galaxy continuously, forming a background that tells a quiet story about energy, motion, and time. Numbers whisper more than they speak, and Voyager listens to these whispers with instruments designed decades earlier, for a future no one could fully imagine. Voyager also measures magnetic fields that are no longer shaped primarily by the Sun. Inside the heliosphere, magnetic lines of force bend and flow outward with the solar wind. Beyond it, the magnetic environment reflects the structure of the galaxy itself. The changes Voyager detects are subtle. They require long-term observation rather than momentary confirmation. Space rarely gives us simple answers, and the transition between solar and interstellar influence reveals itself gradually through consistency rather than clarity. The heliosphere itself remains a central focus of Voyager's interstellar mission. Rather than marking a sharp boundary, the heliosphere behaves like a breathing system, expanding and contracting with solar activity. Voyager's measurements help scientists understand how this protective bubble interacts with the surrounding interstellar medium. This interaction influences how cosmic radiation enters the solar system and how the Sun exchanges energy with its galactic environment. What Voyager observes is not a line, but a relationship. As the spacecraft moves farther away, the environment grows quieter. Particle densities are low. Changes occur slowly. Instruments that once captured dramatic variations now record steady patterns. Silence is also a kind of data. The absence of sudden events confirms that interstellar space is shaped by persistence rather than turbulence, by long timescales rather than immediate change. At the same time, Voyager itself is becoming quieter. Its power source, designed to last for decades, slowly weakens as radioactive material decays. One by one, instruments are turned off to conserve energy. These decisions are made carefully, with respect for both the mission and the spacecraft. Each shutdown reduces capability, but extends life. Voyager does not stop suddenly. It fades gradually. Communication grows more difficult as well. Signals sent from Voyager take many hours to reach Earth. By the time a response is received, nearly a full day may have passed. The data rate is low, and each transmission carries limited information. Engineers and scientists plan commands with patience, knowing that adjustments must be small and deliberate. The spacecraft continues to answer, but quietly, as if speaking from very far away. Despite these limitations, Voyager remains scientifically valuable. Its measurements provide the only direct sampling of interstellar space available to humanity. Everything else is inferred from distant observation or theoretical models. Voyager's presence turns abstraction into measurement. It grounds ideas about the galaxy in actual data, however sparse. Numbers whisper more than they speak, and Voyager's data, though limited, carries weight precisely because it is rare. There is also a human dimension to this phase of the mission. The teams who work with Voyager today are separated by generations from those who launched it. Knowledge has been passed along through documentation, mentorship, and continuity of care. Voyager has become a shared responsibility across time, sustained not by urgency, but by commitment. The spacecraft continues because people continue to listen. As Voyager travels deeper into interstellar space, its surroundings will change slowly, almost imperceptibly. It will not reach another star. It will not transmit forever. Eventually, its power will drop below the threshold needed to communicate, and it will fall silent. This outcome has always been understood. The mission was never designed to conclude with a final message or a defined end. Yet, the absence of an ending does not diminish the meaning of the journey. Voyager's interstellar mission shows that science does not always advance through dramatic discovery. Sometimes it advances through endurance, through the ability to remain present long enough to notice subtle patterns. It reminds us that understanding the universe often requires patience, measured not in moments, but in decades. In this long silence, Voyager continues to fulfill its purpose. It observes without expectation. It transmits without urgency. It exists as a small, steady extension of human curiosity, moving through a region where change is slow and attention must be sustained. Space rarely gives us simple answers, but it rewards those willing to wait, and perhaps that is the quiet truth of Voyager's final mission. That even as signals fade and data thins, presence itself remains meaningful. A spacecraft drifting between stars, still listening, still responding, reminding us that knowledge does not always arrive loudly, but often in silence over time. Voyager was never meant to come home. From the moment the spacecraft left Earth, there was no plan for return, no orbit to complete, no destination that marked the end of the journey. Voyager was built to move outward, steadily and indefinitely, until its ability to communicate would finally fade. In this sense, it is not a mission with a conclusion, but a motion that continues until it naturally quiets. Today, Voyager travels without guidance in the usual sense. There are no real-time controls, no new objectives waiting ahead. Commands arrive slowly, long after they are sent, and responses return hours later, faint and restrained. The spacecraft does not adapt to new goals. It follows physical laws, momentum, and the simple logic of systems designed to endure. Silence is also a kind of data, and Voyager's continued presence speaks through its restraint rather than activity. As time passes, Voyager's role becomes simpler. Instruments are shut down one by one. Power diminishes gradually. What remains is not exploration in the traditional sense, but continuation. The spacecraft drifts, still measuring, still listening, still responding when it can. There is no moment of arrival waiting ahead, only distance increasing slowly, year after year. Yet Voyager is not empty. Each spacecraft carries a record of Earth, a small collection of sounds, images, and symbols chosen not for utility, but for meaning. These records do not explain humanity. They do not define it. They simply acknowledge presence, that life existed here. That curiosity mattered enough to send something beyond familiarity. Numbers whisper more than they speak, and Voyager's message is quiet by design. In the vastness of space, Voyager is insignificant in size and influence. It will not alter its surroundings. It will not be noticed by stars or planets. Space rarely gives us simple answers, and Voyager does not ask for attention. Its significance exists entirely within the context of human awareness. It matters because it reflects a choice, the choice to explore without urgency, to build something that lasts longer than its creators, to accept that not all journeys return with conclusions. There is a humility embedded in Voyager's design and trajectory. It does not claim territory, it does not seek dominance, it does not rush. It moves patiently, acknowledging that understanding grows slowly and often beyond the span of a single lifetime. The spacecraft embodies an idea that is increasingly rare, that progress does not always require acceleration. Sometimes it requires persistence. Voyager also reminds us that exploration is not defined by control. Once launched, the spacecraft became independent of constant human intervention. Its journey unfolded through preparation rather than adjustment, through foresight rather than reaction. In this way, Voyager reflects trust in physics, trust in design, trust that careful thinking, done once, can carry meaning forward for decades. As the spacecraft continues outward, it carries no awareness of legacy. It does not know it has become a symbol. It does not know it represents curiosity, patience, or restraint. Those meanings exist only for us. We assign them because Voyager reflects qualities we value and wish to recognize in ourselves. Eventually, Voyager will fall silent. Its signals will no longer reach Earth. Its systems will cool. Its instruments will rest. The spacecraft will continue moving unnoticed through interstellar space, carrying with it a quiet record of origin. There will be no announcement of the final transmission, no definitive moment of closure, and perhaps that is the most fitting ending. Voyager does not conclude with certainty. It fades into distance, leaving behind understanding rather than answers. It reminds us that exploration does not always end with arrival, and meaning does not always require return. Sometimes, it is enough to send something forward, carefully and patiently, and allow it to continue on its own, carrying a small echo of where it began.